Okay, we should
Go to
start.
you.
Um, well, um, it's another Friday, and thanks all of you for taking the evening. I hope this will be a continuation that's useful of the discussion that we started last time. Uh, but before anything, there's one thing that I think is very important to do this time that in in other sessions we've had together, I haven't done, and that's a commemoration. Uh, it being 2026, and this being a discussion of spectroscopy, as it's been for so long now, uh, it's very appropriate to start the discussion today with a commemoration of the centenary of, well, what we'll call modern astrophysics. That is, uh, just 100 years ago, Cecilia Payne-Gaposchkin and Arthur Eddington and Hopkins, Jeans and Milne and Rosalind and others and Stromgren, but specifically Eddington and Payne-Gaposchkin, then Payne, founded in a very real sense what became modern astrophysics. Eddington with the publication of his monograph, The Internal Constitution of the Stars, and Payne with her analysis of the ionization structure of stellar atmospheres. So simultaneously, you had the beginning of a global view of what is involved with the structure of stars and consequently stable objects, and also how to analyze them properly. We could add to that the publication of the Treatise on Astronomy by Russell Dugannon Stewart, which is famous for the introduction of atomic classification schemes to a broader audience. It was essentially the 2 volumes of their work on astronomy, which was an update of an earlier work, also from Princeton by Young, that had reigned in the field for 20 years and contained almost nothing of a discussion of spectroscopy at all. That before even Russell, but before the 1920s, if you were talking about astronomy as a field, it was either photometry, which could be done either by eye or by photographic plates, or by the 20s, photoelectrically, or you were talking about determination of dynamics by orbits and astrometry. And the idea that you could actually use spectra to drag physical information out of remote objects was something that was just beginning to take hold. See, the problem, we haven't really talked about this before in the same way. The problem with interpreting stellar spectra isn't that they can't be classified. And I'm talking specifically about stellar spectra, not spectra in general for the moment. That the absorption lines that you see in the stars that have MK classifications, in other words, the ones that can be placed in some kind of a uniform taxonomic order where you have complexity and specific species as your tracers, essentially something like taxonomy in biology. Those don't require any specific explanation because they're just labels. If you've got spectral types, and I really want to emphasize this for our discussion over this next session. when somebody gives a spectral type to an object, the only thing that that really tells you is the spectral type of that object. It's only with ensembles of spectra of other objects for which you can absolutely determine the properties that you can assign any more physical meaning than descriptive to that spectral class. Now, all of the last century has gone into that second step. The classification systems had already been worked out as early as the turn of the 20th century when the Harvard system was introduced, that is the HD, that became pretty much the standard across the business by virtue of it having been applied by the 20s to just about every bright star in both hemispheres. But to say that it was anything more than a type was actually not physically meaningful until it was somehow correlated either with laboratory measurements or with physical theory or both. And after the beginning of the 1920s, that was in fact the main thrust, to look at stars as hydrostatic objects. And by that I mean mechanically stable objects, which had already been argued for the sun even 50 years before and demonstrated to be something something verifiable, that the sun had been around for a hell of a long time, much, much longer than any of the dynamical times associated with the sun. And so you could say, well, it had to be in mechanical equilibrium. And historically, it was known that the temperature hadn't substantially varied, at least since the time that the Greeks were running around in togas. So it was another step of saying, well, okay, you've got a thermal time scale that we can measure in millennia or even millions of years. Consequently, we also have thermal equilibrium. And over time, it was realized that there were pulsating stars. At any rate, the idea that a star could pulsate rather than just orbit and eclipse had already been worked out in the 1920s as at least a possibility that if you've got a fuzzy ball of gas and it, for some reason, gets perturbed, so it compresses a little bit, it'll expand back out and it'll oscillate. And so one of the modes that you can imagine for stars is a pulsator, but that's stable in the sense that if you take a time average, the pulsations average out. At least that was what was thought. And so as long as you could assume that something had pressure balance and thermal balance, you could think that you would be able to structurally disentangle the run of temperature and density inside the object. And so understand when you extrapolate that out to the surface and then beyond the surface through the atmosphere, what the composition and physical conditions were in the atmosphere. And so from that, infer what the conditions were in the interior. That was the whole point of this pair of events in 26 and 27, that for the first time, it became possible to join what was observable, that is the atmosphere and the surface, with what could presumably be going on in the interior, that is the structure, without undue undue speculation. So what I was hoping we could do today, and I hope I'll make this clear, is to talk something about how one goes about analyzing stable spectra. The last time we were talking about dynamics, winds, ejecta, jets, and that sort of thing. But most of the objects that will give you the most insight in into the no, let me put it differently. If you want to understand a population, you first have to define what is the average person. You can do that by standing on street corners. We do that by standing on a street corner 8 kiloparsecs from the galactic center, and we kind of watch things go by. And we sort of have a neighborhood, and so we know who's living there. And we presume that by an analysis of that population, assuming that we're not in some tremendously special place in the galaxy or in the neighborhood, we can figure out what the bulk of the stellar population of a galaxy looks like. And if we understand it for our galaxy, then we presume we can understand it for other galaxies as well, where we're not going to resolve the individual stars. So the first thing we have to do, if we're going to do astrophysics that extends beyond merely the sun and the solar system, if we're going to really extend the scope of astrophysical studies to the limits of our ability to obtain verifiable data, we've got to understand how to apply the physical picture. Sorry, we have to understand how to extract from the data that we have as much physical information as we can that we can then compare with the stars in the local neighborhood so that we can then extend what we've learned from the local neighborhood to these external objects. I hope I've made that clear because the whole point I'm trying to get at is that if we want to understand the evolution of the universe, we can do that at least in the local region, meaning within the range of resolved galaxies, only through stars, singly or collectively. As we go progressively farther away, we don't have to go very far still. Even at a couple of megaparsecs, we lose the resolution to see in most individual stars, except for the bright freaks. Most of the time, we can't even distinguish whether they're single or multiple. So to do that, to extract that kind of information, we're going to have to understand how spectra are formed and how they're analyzed. And because the bulk of the population is not going to be peculiar by definition, we also have to understand what's normal. I hope I've made that clear. So let's go to to a screen share. Um, I hope, let's see. So, okay, I just want to make sure you can see now a spectrum on your screen.
Yes.
Yes, yes, we see.
Okay, so I'll start first with, let's see, preview. So let me start with something that you already know from all of our other discussion, that the there are two things that there are two processes that contribute to the formation of spectra. That is the energy distribution that we call a spectrum. One of them is continuous, which means either ionization or recombination or something like it. That is where one of the characteristics is that there may be a threshold to the process, but then any energy above any photons with energies above that threshold, any can produce some ionization or some dissociation. That is, it's not, in other words, it's not discrete. Okay? All other features of the spectrum are discrete, whether they're straight absorption, whether they're fluorescence, whether they're scattering, they take place through atomic lines. And this means that all of the processes, including the continuous processes, depend on temperature and density. And so, in the hope that I can get this to work, um, okay, this is a little bit more awkward than usual because when the pad doesn't exactly work, it becomes a little bit more difficult to move things around. So let's start with a basic point that if you've got an absorption line simply means you have something that's dark seen against something that's bright in an energy interval that is determined by the atomic structure. That's a lousy way of putting it. Let me put it much more simply. When you see a line, it's because you have a discrete transition between two energy levels, period. If one of those happens to be the ground state, then its absorption, that is, the rate at which a medium in that state can absorb light, won't depend on temperature. That is, even if you have the equivalent of cold matter, so everything is de-excited, you don't have collisions, you just put an atom or an array of atoms in the way of a beam. Okay? When you look at that beam, if you're off of the line, you'll see some energy, like looking at a lamp. But when you look at the frequency of the line, you'll see less light. And the more crap you've got in the way, the less light you're going to see within the interval in frequency or wavelength in which that atomic transition or that molecular transition can absorb. This is actually almost a triviality that as long as you can put a source behind an absorbing or emitting medium, what you see is the effect of that medium on the light from the source. That's what we mean by an atmosphere. Okay? It's just a layer that sits on top of a region that's more opaque. So until when you're looking through a medium, when you're looking into a star, and this was the whole point of Payne's thesis. This is why I said it's the combination of these two that created astrophysics. Let me stop the screen share for a minute. When we talk about seeing into a medium, what we mean is we're going to look through the gas, it's an atmosphere, down to the point where we can't penetrate. Now, if there's light coming from below, which is Eddington's part of the story, if you've got this big ball of gas, then there's some point where, since it's pressure balanced and compressible, the two key points, as you move away from the center, you have less mass above you, it's less compressed, period. So, if you have a self-gravitating ball of gas that is able to, and as I said, that's self-gravitating, so it's able to support itself by the compression due to gravitation producing an internal reaction that raises the pressure. If this were a perfect gas, then the temperature in the center would be higher than the temperature in the periphery, the actual gas temperature, and the density would be higher in the center than in the periphery. And so there you go. You've got radiation that's going to stream out from the interior because the little bugger is cooling. There will be some point from which the light will be able to exit. This is the same thing we were talking about last time with the idea of a random walk of the photons. Eventually, they see the sky. They see the outside, and that's where you're sitting. So, what happens, because they don't just make a transition as if they were on a plane or on a board, they don't just jump off into the vacuum. This is a continuous medium of progressively decreasing density. So, you have a surface which is bright, and then you've got an atmosphere above it. And what you see is simply the imprint of the composition of that medium called the atmosphere sitting between this most opaque surface and you. Okay? That is a stellar atmosphere. The difficulty comes at this point with understanding that because this is a real gas, it's not going to be one temperature because it's a compressible gas. It's not going to be at one density. The base is going to be denser than the higher layers. The base will likely be hotter than the outer layers. As the transparency increases moving outward, you would also expect that it would actually be able to cool better. So the atmosphere is going to have some energy lost relative to the deeper layers. Now, the problem is that you would think, from what I had just said, that if you had a resonance line, so everything is starting from the lowest level and just absorbing, okay? And then scattering the light out of your beam like looking at a laser through a cloudy room. If you look at the line and everything were just from the ground state, then the only thing that would matter is how much garbage is sitting between that opaque surface and where you are. And there would be no temperature dependence, you would think, in this medium. So if you compare the strengths of lines, it should be proportional to how much stuff you've got in the way. And if you compare, say, lines of iron with lines of helium, that should say, well, if the iron lines are stronger than the helium, or if the iron lines are stronger than the sodium, then amazingly, there must be more iron than sodium in that object. At least that would be the way you might think of it in chemistry, that you look in the beaker And you look at how much light is passing through, you get a spectrum, and that tells you how much of, say, iron or magnesium or vanadium you have in your sample. Okay? That works in the laboratory because laboratories are damn cold. But if you try using the same logic for a star, any astrophysical object worth its salt, you got a problem that the energy levels in atomic systems, especially neutral and ionized atoms of the iron peak, those have a problem that if you're at a few ten, it may be 10,000 Kelvin, something like, say, Vega, the temperature coming from comparisons with laboratory energetic and spectral standards. If you look at the spectrum as you would have it in the laboratory, there are thousands of lines with energies of only a few electron volts. That's a real problem because those are excited states. In the laboratory, everything is coming from a cold medium, so you're pretty much only seeing the absorption from the ground state transitions. It's one of the reasons why spectroscopically it's so hard to study helium in absorption in the laboratory, that to study most atomic lines, most species, you actually put them through an arc. You put them in an excited state so they emit. No arc lamps. You've used them for comparison lamps. Okay? If you think about it, if you had to do absorption from neon or argon or thorium instead of using emission as you do, that would be a real problem because the lines from neon that are coming from the ground state are in the ultraviolet and they're not very useful for you. But if you put a current through it, you can excite the system because of collisions. So you can see the lines in emission. But you don't see those lines in emission in normal stars. And that was why it was so important that Payne was able to apply a correction for ionization. That the reason hydrogen lines and iron lines, for example, in the spectrum of the sun, look very similar in strength is not because there is so little hydrogen relative to iron, just the opposite. It's that the iron is selectively visible because it comes from lower states, that ionized iron and neutral iron have strong absorbers at the wavelengths at which hydrogen would not be able to absorb from the ground state, that the hydrogen lines that we're seeing are coming from 10 volts. They're the Balmer series, Paschen, and so on. And so it's not that there's no hydrogen, it's that it's a weak absorber. It's not a weak absorber intrinsically. It's only because you've got a hell of a lot there, but you're sampling only a very tiny fraction of what's there because you're looking at the wrong transitions. If you look in the ultraviolet at the Lyman lines, there's no problem. You see the absorption all over the place. The only problem, of course, is we don't see the UV because of the Earth's atmosphere. So you'd have to get above the atmosphere to see it. But Payne's solution, and the thing that's going to be important in our discussion, is that it isn't simply the strength of the line that matters. Now, let me explain another another piece. If you have an atmosphere like the Earth and you view it from space, you know from experience that the temperature of the air at the top of Mount Everest is a hell of a lot lower than Sicilia in August. Okay? That no matter when you go up to 10 or 15 kilometers, it's going to be uncomfortably cold compared with being at sea level where it may be uncomfortably warm. Okay? Simple. But think about what this means. If you have a uniform composition of that atmosphere, lines from species like hydrogen, or let me take a simpler example, just one that where the ultraviolet is where the main lines are. And in the visible, we're only seeing from excited states. Then those lines are going to be primarily formed in the lower atmosphere where the temperature is higher. The lines that are coming from the upper atmosphere would be, in this picture, coming from lower states. So if you look in the visible, you look right through them. Okay? They're not there because that part of the atmosphere is incapable of absorbing at those frequencies. Okay? All the lines are in the ground state. But if you've got some excited state lines, they're going to form in the lower atmosphere. So when we look at a spectrum, the strength of the line is actually an indication, at least a signal of where it's formed in the medium. If we don't know that, the strength of the line alone does not give us the abundance, nor does it give us the atmospheric structure. But the comparison between lines of the same element and different states, that is, different ionization states and different excitations, maps out the actual structure of the atmosphere. So if we have the ionization structure and the excitation structure, we can actually determine the abundance. We can actually determine the pressure and the temperature and predict what we would expect to see for the other lines in different parts of the spectrum. The reason for going through this is, is the question that we're addressing. A fundamental question in understanding galaxy evolution, perhaps the fundamental question, if you'll accept my bias for a moment, is what's the origin of the elements and how do they change in relative abundance over time? That was a question that began 70 years ago in earnest. It took a long time after Payne's work, Unsold, and a whole raft of Mihalis eventually. Those who were building the picture of how to analyze a stellar atmosphere were driven not just by the first question, which was understanding the taxonomy that I just mentioned, spectral classification, but how the elements trace the history of star formation. And ultimately, if you really want to get, science fiction-y about it, if we understand how the elements have increased, then we know something about the origin of life. It's important to make a comment here. When I say the things we want to know, Those are kind of collective community sorts of questions. When you're doing spectroscopy, it can start as pure curiosity because there's this panoply of objects with wildly different spectra and many different properties. And so pure curiosity can be the driver. You just build up experience in seeing what this population looks like. And it's basically the same as going into a forest and just enjoying the view. But if you're trying to drag more information out, then there have been questions defined by the collective work on the astrophysics for the last century that lead to certain techniques of analysis and certain classes of inquiry. Okay? And that's why I'm emphasizing abundances and structure and stationary objects. Last time we were talking about how you use spectra to understand dynamics, internal flows, explosions, stuff like that. But those are rare events. They're also transients. And the majority of objects that have been studied over the last century are stable. They're stars. But to get to the next point that we'll be discussing today, I need to make one thing clear and drive this home to all of you. Spectral classification, the analysis of stellar atmospheres, the determination of abundances in standard theory and our general understanding works for stationary objects for which the structures observable are time independent or damned close to it. That if you try applying classification based on stellar spectra like MK or anything related to objects that are transients, you are making a grave mistake. Okay? That our understanding of spectra, our understanding of stellar atmospheres, assumes time independence. If you don't have that, if the object is pulsating or if it's expanding like in a wind, if it's stratified differently than it would be under hydrostatic conditions, you are making a fatal mistake in the application of classification schemes. I can't emphasize this strongly enough. You can get two stars, one of which has a strong wind and the other is absolutely stable, that at one time or another look exactly alike. And all that tells you is that what you're looking through has the same physical conditions locally. That is, the same pressure, the same temperature, and the same density, at least as far as you can see it. But it says nothing from that comparison alone about the physical conditions in the object itself. It only tells you what is in the medium that you're able to sample. So, having gone through that polemic, you've been very kind. Let me give you an example of the way that such an analysis would proceed. So, what I'm going to set up now is a set of absorption lines. Let me see if I can. Do we have the whiteboard? Let's try
Excuse
that.
me, Steve, I have a question maybe.
Please, please.
Um, yes, in a pulsating star, we could make maybe the assumption that the abundances are the same. So if we measure the spectrum at different steps of the variation, we could maybe use this information to gather knowledge about the real abundance at different altitude in the atmosphere of the star in comparison to a static star where
Huh?
we just have one screenshot with all the abundances melt with all the different conditions depending on the altitude in the atmosphere of the star?
It's a beautiful question, and the answer is maybe. That the problem is if you have a stationary object, you at least know what the vertical structure is, okay? Because it's stationary. It has to be in a kind of pressure balance. If it's pulsating, for example, the velocity of the different layers will be different. It's not that you have something that just goes up and down, okay, like a spring. It's a spring whose springiness depends on depth. So you don't have just one frequency. You know, if you take a slinky, a spring, and you extend it and then just start shaking it on the top, you're going to notice that the different parts of the spring are vibrating at different frequencies. Okay? Now, if you've got the photosphere doing that, okay, then the layer above it may have a different phase. It will have a different velocity because it's not a shell, it's an ensemble of shells. So at any moment, they're individually changing their densities and pressures, consequently, temperatures. Now, if it's a truly stable pulsator, then you can come back one period later and it should look the same. So that's why I said maybe. If you can follow the cycle, then you can figure this out. Okay? But the problem then becomes looking at a whole spectrum rather than, say, just a couple of lines. Because at some phase, think of a Myra variable. At one phase, you have a very extended photosphere. And above that, there's an extended atmosphere. When the temperature of the photosphere drops, so does the excitation of the outer layers. They can turn very opaque because of molecules, where when it's more compressed, one half cycle later, and the temperature has gone up for the photosphere, the atmosphere may be more compact. And so it may be less opaque, which means you're seeing deeper. So, relatively speaking, you're always looking not only at different layers, but different layers that are changing relative to each other over time. This is one of the hellish things about working on pulsating objects. If their amplitudes are small, you're okay. That is, it's like looking at a little ripple wave on a lake, that the surface doesn't really change much. You're pretty much always looking at just a surface. But if the wind is blowing hard, if you have really intense waves, then it's very hard to define where the surface actually is. It's sort of the same thing when you're talking about stellar pulsation, that stars like the Delta Scutis, where the velocity amplitude is very small, the periods are less than an hour, those are linear. And we can pretty much average out the pulsation and just look at them almost as if they were stationary atmospheres. But if you look at a Cepheid, it's not true. At that point, the surface may have velocities that are tens of kilometers per second, but differ from one part of the star to the other, that is, one part of the atmosphere to the other, by tens of kilometers per second. And for RR stars, it's even worse because those have such large amplitudes that when one layer is moving outward, another layer may be moving back in which case they're going to compress and shock. And so you can get emission lines formed from something like that. They're never exactly the same because you have this interplay because of this phase shift. Now, if you've got a wind, it's just as bad. The wind may not be stable, may not be stationary. And I wanted to emphasize that actually in the context of analyzing a spectrum. Let me see if I can, I hope, find the image that I wanted to use. Okay. Um, so, so going to the screen here. Okay, I hope you can see this
That's
now.
okay.
Okay. Um,
Yeah.
these are three totally different objects. I was showing this to Francois before we started. It's one that I'm currently working on with Remo Di Giacomo, whose whose work on Novi was a thesis last year. The top object, this one, is Novacast 2021, which was a nova. It was a slow nova, behaved more or less normally. At any rate, it didn't disappoint. But the second, Gaia 22 ALZ or AL Zeta, was probably a slow nova. There's a paper from a couple of years ago by ID and Company that ended with equivocation, but more or less probably a nova, except it was like three times slower than V1405. And the bottom was a symbiotic star that went through the equivalent of a heart attack and was a nova in 2010. Now, two of these, this is as far as you can get from equilibrium, and that's why I'm showing you this. If you came up with a classification that says at a particular stage in a nova, you should always see this kind of line profile. That is, an absorption that's shifted to high velocity. These are iron lines. That's iron multiplet 42, but that's not the important point here. It's that the only thing you're getting out of these two spectra, it's important, but the only thing you can say for certain, aside from this is obviously a glitch in the spectrum, is that the conditions that produced this pair of spectra are damn close to each other. Similar densities, similar temperatures, similar ionization states. That's all you know. The objects could be completely different, but they're clothed the same way. Using that as an analogy, you can think that you can have two people, both of whom are wearing gorilla suits, but one of them is a man and one of them is a woman. The gorilla suit is the same, But as soon as they take it off, you know that there's something different underlying them. But you saw the same gorilla suit. Okay? Could have used elephants also because, psychologists talk about the gorilla in the room. Well, there's the gorilla in the room. They're clothed the same, but the underlying source may be different. The only thing that you know is the conditions under which these spectra were formed are similar. So we go down to the bottom spectrum, which doesn't look very much like this, except there's a coincidence of a pretty fair number of the lines, if you notice. They're not the same, and there are a hell of a lot more lines, these very weak ones. This says that the ionization state was similar, but the physical conditions of density and velocity were different. These very, very weak lines that don't correspond to something here are all forbidden lines. Again, the only thing that tells you is that the medium in which this spectrum was formed had similar ionization conditions to these two, but it was a different object. Okay? Having certain ions tells you about the internal energetics. It may tell you about the radiation field that produced that spectrum, but that's all it tells you. Now, going to a different spectrum, this is a closer comparison where now you see the profiles are also different. That, for example, on this line, which is a helium line, this is H beta, this is helium. You see that the emission line is very similar, but one of them, that is Gaia, shows an absorption and the other doesn't. That is V407 Cygni. Or here, where the wing of the line in emission is different than the wing of the line in the other star. And yet, you notice every one of these finds a correspondence in the V407 Cygni spectrum. So, what this tells you is that you can use, if you can analyze the physical conditions that give you the lower spectrum, you can use that to place constraints on the upper one. This one we understand, this one we don't. Okay? So automatically, just looking at this comparison, you take a spectrum, high or low resolution, compare this to, say, a planetary nebula. And the first thing you see is in Gaia, there are no forbidden lines. So the density has to be higher. Even if the ionization is the same, the forbidden lines are being damped by collisions. So you've learned something. If you try to get the abundances of elements or the relative abundance from the line strengths, you know that you've got to use a high density approximation. If you're trying to use the hydrogen lines, you know that it's going to be an opaque medium just by the comparison. Now, another example is here. Yeah. Again, um, this is one of those times that I can show you what will be coming. We talked a long time ago about T-core Bohr. Uh, it periodically gets written up in bathroom graffiti. Uh, it's one of these that this is a comparison between that same spectrum that I showed you of 407 Cygni and this time something that's basically the same thing. That is a high resolution spectrum from ASO of the 2006 outburst of RSOF. RSOF is also a recurrent symbiotic. And what the comparison tells you is, yeah, they really are basically the same. There are differences in the relative strengths of the lines. They weren't taken at exactly the same phase in their outburst, but all of these very narrow lines, they're all here. The broad lines, they're similar. They're not identical. So this tells you from the width, you can determine from the differential width that one set, that is, the narrow lines, are coming from a region that may be very far from where the broad lines are formed, or it may be almost mixed, almost, but not at the same place. Because all the forbidden lines, the low density stuff, all are narrow, and the permitted lines are very broad. The permitted lines also have a narrow component. So you have, from this spectrum, immediately you see there are two regions. One is a narrow region, narrow line region of low density, the other a broad line region of higher density, because none of the forbidden lines show up as broad lines. You see, now you've got structure and dynamics from the comparison between two spectra, or even one once you know how to read it. So, what would be important here is the relative widths of these lines to pick the narrow component, for example, by using some of these forbidden lines, and then compare that to the broad. And that gives you the relative dynamics between these media. Okay? Now, this is in dynamics. So let's talk about what happens on the other side of the business when we're looking at straight absorbers. If you're looking through an atmosphere, no, I'll do it simply. Look through a cloud. You imagine that you've got a star seen through the interstellar medium. Now, a great example of that actually is so um, 5800, 5950. Okay, so I got to change screens, right?
Well, no,
You know,
no.
there is something tremendously annoying about having to constantly go from one screen to another manually.
That's okay.
Okay, so um, this is a spectrum of a nova. Again, it doesn't matter. With this time, I'm going to tell you, it doesn't matter what you're looking at. Okay, this is a star somewhere off in Never Never Land. But these very, very sharp lines are the sodium D lines, that is the doublet, in the optical, formed from the interstellar medium. Now, this is a cloud, and um, so Okay, so there are two lines here. They come from the ground state of neutral sodium, and you see that they have different depths. And that's not just because of the emission line against which they're absorbing. Okay? I hope that's clear.
Yes.
The different depths are because they are the same species. They are coming from the common lowest energy level, but the lines themselves are to slightly different energy levels. One of them going to a higher energy than the other. And in fact, they have slightly different intrinsic strengths. So the amount of light being removed by by these two, relatively speaking, must be different because one of these, this one, the D2 line, is an intrinsically stronger transition than the D1, but otherwise they're identical. Now, the comparison between these then becomes important because by saying that the opacity, meaning the intrinsic opacity, should be higher for D2 than for D1, means that the amount of light being removed by these for the same column, because you're looking at one species through a cloud. The amount of sodium you've got in the way is what determines how much light is being absorbed. If the ratio of these two lines is the same as the ratio of their atomic strength, to put it in technical terms, you would say if the oscillator strengths are the same for these, the ratio of them, the intrinsic strength, is the same as the ratio of the amount of light removed, then you know that all you need is one of these, and you know how much light has been removed, translated into how much garbage you've got in the line of sight. This is the origin of something called the curve of growth method, and you probably know this as the determination of the equivalent width, which simply means the relative amount of light that's been removed from the line of sight. So to show you an example of what that means, let's do a little simulation. Imagine that you've got a single line that you're for which you're looking at different column densities. And I have to change screen here. Um, Hoping that I go to the right one here. Um, okay. I'm okay. I apologize for this. I'm kind of lost in multi-window land. So, okay, you see, okay, if I go here to window 2, okay, you're seeing blank now, right?
Yes, right.
Okay. Now let's imagine that we have that line and we crank up how much garbage we've got between us and the source. This is what you'll see. As the abundance goes up, as the amount of material goes up, the line gets stronger. But you notice the rate at which it's increasing slows. That's called saturation. But the wings of the line grow. In this case, it's not the actual values of what I'm using here for the model don't really matter, because this is a generic behavior that the wings are coming from the atomic line itself, and some of the broadening in the core is due to random motions. Now, we talked about this a while back, that when we see a line formed from any medium, an atmosphere, a cloud in the interstellar medium, or even the intergalactic absorbers in the Lyman forest, an atom has a motion relative to us, a radial velocity along the line of sight. If it's in an ensemble, that's a random motion. There may also be a uniform motion, like when we were talking about winds and ejecta. But within the medium itself, there's going to be some random motion, both from thermal and from some macroscopic random displacement. And that broadens the line. Instead of seeing just the wing like this, we also see a smoothing effect because every piece of this profile has been broadened out. Depending on how broad that is, we may in fact change how the line develops. So to give you an example of that, if I simply make the medium turbulence, give it a macroscopic motion, I'm running through the same column now, but you see that it's not even yet saturated at the end. And if I broaden it out even more, again, because of the random motion, you see that now we're not even close to being saturated. In other words, we would, if we couldn't resolve how broad the line is, we get the wrong abundance, because the amount of light that's being removed here is different for the same amount of material as when the line isn't as broadened out. Okay?
Yeah.
So the equivalent width tells you something about how much material there is, and the comparison between lines of different equivalent widths becomes an important measure of how much material there is, since there should be a relation between the absorption and the column, but there are other things that can affect it. Now that's in a single cloud. Frequently, actually, the plot so this is the amount of energy that's been removed, and this is a measure of the column. At first, it increases linearly, more along the line of sight, the stronger the line. But then saturation sets in. And so if you see a line at a given strength, you would, if it were behaving the way I'm showing you, you'd be able to go from that strength directly to an amount of the material along the line of sight. There's a problem with this, though. You've made a very big assumption. The one that distinguishes today's discussion and where we started in with Payne and Eddington and the discussion from last time. You're assuming that you're looking at a layer, that it's just a layer, uniform, no change, no gradient in density, no stratification of temperature. So as the column increases, you just have more stuff. You know damn well that that's not true. Again, because when you're looking at the Earth at the top of Everest, the temperature and density of the air are different than they are from the base. So one of those you are looking through to get to the other. That's as true in this line profile as it was on Mount Everest. The wing of the line, and this is important, the wing of the line is less opaque than the core. Just looking at it, that's obvious. That also means that you're looking deeper when you're looking at the wing of the line than when you're looking at the core. Here, you're sensitive to what's going on in the upper atmosphere. Here, you're sensitive to what's going on in the lower atmosphere. When the line is weak, if you see the line at all, it's because you're looking deep. You've got to have more crap in the way to actually see the absorption if the line is intrinsically weak. And that requires you to be looking into the densest parts in the medium. So the line profile isn't simply a result of one width of the line and one strength of the line and one excitation and one level and one temperature. It is the integral over the whole atmosphere along the line of sight. That's why the problem's hard. But that is why when you look at a spectrum and you give it a spectral classification for a star, you're really compressing all of that information into one name. If you say that you're looking at at a B84 star, for example, so B8 subgiant, that's all you know that you're looking at. You could have two spectra that have the same apparent line strengths, but they might not be coming from the same object. On the other hand, when we've looked at enough of these, as happened with spectral classification, you see that there are tremendous regularities. The whole reason that taxonomy works for stars is that the little buggers are simple. The reason that it doesn't work for anything dynamical is because they're not. Okay? It's just a summary way of putting it, that the reason we can directly interpret from strengths of lines the abundances in stars with some effort is because we can compare the lines from different ions and the lines from different levels that give us the combination of ionization, which is pressure and temperature, and radiation, and broadening, which is pressure and temperature, and excitation, which is pressure and temperature. And by comparing lines of different ions, one of them is formed in a different depth than the other. If they're the same element and and homogeneous, then we can figure out how to correct for the fact that we are looking through a composite medium. And this gets back to the question of stellar pulsation, that if you've got a pulsating star, at any moment, you're not looking at any one of these atmospheres. You're looking at something that's much more complex. Now, there's a big assumption here that there's an assumption that may, in fact, break down. First, homogeneity, first and foremost. When we talk about trying to obtain the composition of stars, to understand the chemical history of the universe, we're assuming in all stellar evolutionary models, in all of our understanding of the interior, that the surface is indicative of the interior. That's the combination of Eddington and Payne-Kapashkin. And again, that's the reason that I started with this. The fundamental assumption, if we're going to make use of the atmosphere at all for determining something about how stellar evolution affects the synthesis of the elements, is that what we're seeing on the outside is indicative of the bulk of the interior. We know damn well that the interior, the very core, is changing over time because of nuclear processes. But we would presume that, at least in relatively normal stars, the reason that taxonomy works is because the abundances are uniform through the line-forming region. At least that, at least down to the photosphere, and maybe below that. So the upper envelope at least has some constant abundance. We don't have to worry about gradients. That's not necessarily true. We can test that by precisely the failure of the procedure that I've just talked about. You take lines of the same element and even of the same energy level and or nearly the same, and you compare them and you see whether they give you a uniform structure or you require that each one of them has a different atmosphere. It's a very slow, painful process, and it requires models, and that's why I'm only mentioning it briefly. But this idea that you can go directly from the equivalent width to an abundance makes very, very strong assumptions. And those work approximately for the majority of stars, but not exactly. Okay? But it does tell you, by looking at the way the curve of growth behaves, what you can read out of the line profile. Again, if I had this, let's say this is from one layer. From another layer deeper down, where I may have less of this ion. For example, this could be neutral iron in the outer atmosphere, and then in the lower atmosphere, it would be ionized iron. That would mean that we could have the same abundance of iron between two stars, but the hotter ones will show a stronger line than the colder one. Very simple, because the colder one is going to have more of the neutral species, and the hotter one will have less of the neutral in the atmosphere and more of the ionized. Okay? So I hope that makes it clearer. Um, Let me change screens yet again. Okay, so um, this is a transient, but except for the emission lines, and yeah, this looks like it is a really lousy spectrum, but I can assure you, uh, virtually everything you see here is lines. Uh, if you looked at this and you had the right kind of bias in your training, you would immediately say, "Oh, wait a minute, this looks just like an A." Well, not like an A star, maybe like an F star. Yeah, sort of like an F star. That is, you've got the Balmer discontinuity here. So this is the ionization in the UV. Uh, if you really stretch your imagination, these are atmospheric bands. So um, those of you who have seen The Wizard of Oz will remember the line, "Ignore the man behind the screen." So just ignore the screen in front of the man here. The There's a transition here, another edge. That's the Paschen edge. So this is what I meant by continuous spectrum. And then there's the photosphere, which is here. So zooming in, um, so which window is this? Okay, I'll just stick with this. That in this case, this would be what you'd get from a low resolution spectrum. You might think that you can classify this. This, by the way, is just a gap between orders, as is this. This is an ESO spectrum. But that what you need to understand in this spectrum, let me please pardon my hesitation here for the moment. I just need to go back a moment. Okay, now I got it. Okay, so
Okay.
this is now a zoom on that spectrum. What you see from looking at it is that there are, aside from a gazillion lines, there's this converging series that you know intimately, namely the Balmer series. So going to slightly expanded view, leaving aside the peculiarity of this being multiple components in the line. Uh, the point is, you see that there's a convergence of the lines, and you can see the Balmer lines to a very high number, much higher than you would see in, say, a star like an F star that was an F main sequence star. In fact, you can count up to about,
Yeah.
12 or 14 here. That tells you you're looking at a medium of low density. not anywhere near as low density as a nebula, which is what you were seeing in V407, but the last visible hydrogen line is an indicator because of the broadening of the lines by collisions of the density of the medium. In BE stars or shell stars, one of the signatures of the shell is that you see lines up to Balmer 21. You see the same thing in giants and supergiants. An extended atmosphere will give you the absorber. There's strong lines, but you see lines to a very high order because they're narrow and they don't overlap. Okay?
Yes.
Now, again, in the same spectrum, what had been absorption lines elsewhere is now bloody composite. Okay? That these are the iron lines at 5150. It's my favorite multiplet. Um, 51, sorry, 4921, 5018, and 5169. But you see, there are all of these other absorbers, some of which show the presence of emission, meaning an extended atmosphere that's optically thin and not seen against something. As we talked about last time, when you see emission lines, there are two possible explanations, and only two. One, you know perfectly well from looking at images of the Earth seen from space, that you've got the sun shining onto the Earth. Some of that light is scattered, and the scattered light is then seen from the outside, not in the direction of the sun. Same reason you see clouds looking bright. That if a cloud goes in, again, if a cloud is in front of the sun, it looks dark. It's not that it's cold, it's simply dense. And it's not emitting as much intrinsically as the light that's passing through it, as the source you're seeing. On the other hand, when you look to the side, in other words, the cloud moves off the sun, then it looks bright. And the reason is it's not absorbing against anything, except, of course, the sky. But you got this light source that's scattering into your line of sight. So a reason you can see emission has nothing to do with temperature or pressure. It's just a density effect. Okay? On the other hand, when you look at the sun, and you know this from countless photographs in H alpha and in the emission lines, there's this thing called the chromosphere and the corona, which show emission lines. Strong emission lines, in fact, they're genuinely hot. So there are two fundamentally different processes that can produce the same profile. One of them scattering, which is not necessarily thermal, and the other thermal. If it's not thermal, all it means is we've got more light coming out in that transition than the source along the line of sight. So this is if it's scattering, it's not local. If it's scattering, it's not heating. But we teach at a very elementary level, meaning when we're all vulnerable, we learn Kirchhoff's laws for the formation of spectra, one of which is a cold medium in front of a hot medium absorbs, a hot medium in front of a cold medium emits. Okay? And so you immediately associate the presence of emission with temperature. That only works if the medium is stationary and collisionally dominated and a normal atmosphere. In which case, if the temperature goes up in the outer atmosphere the way it does in the chromosphere, seen against the surface of the sun, the line will appear in emission. Okay? Normal stars don't look like that, or at any rate, they're not strong. The chromosphere is a very weak part of the solar emissivity. It's very important for us, but that's another issue. On the other hand, to say that the medium might be scattering, that you could see an emission line, is the same as saying if you take the spectrum of a cloud in the Earth's atmosphere, intentionally, by the way, so you deliberately go out at night on a night when you normally wouldn't go out because it's cloudy, and before sunset, you take a spectrum of the sky, you're going to see the solar spectrum. It doesn't mean that the atmosphere has suddenly gone to being 6,000 Kelvin. I mean, we're currently living through war conditions, but so far nobody has blown up nuclear weapons in the atmosphere. The only thing is you're seeing a scattered solar spectrum, but it's an emission. At least, excuse me, the cloud is brighter than the background. Okay? Both of these are contributing in the formation of a stellar spectrum. Scattering is typically less important, excuse me, when the medium is not very extended. One moment. On the other hand, so if you've got a very compact or relatively compact atmosphere, then you're going to see absorption lines.
Don't,
It's that season. If, on the other hand, you have a very extended atmosphere, as you would with a red giant, then the outer layers may be scattering. And so the behavior of the lines can't be interpreted as reflecting immediately the density and temperature locally, which is the other point I wanted to make as a central point today. You have to have some idea of what you're looking at before you start interpreting the spectrum. This is the sort of thing you can measure: velocities, relative profiles, absorption. Okay? You can get emission equivalent widths by just measuring how much relatively is coming out in this emission feature. But that doesn't tell you anything except the relative strength of the line. A fourth thing is if I can use now, I want to try the whiteboard. Let me see if this works. Okay. So you see the whiteboard here?
yes.
Okay, good. Now, um, if you've got, say, two stars in a binary system, so one is orbiting in front of the other.
Mhm.
Okay? If you're doing photometry, then you pretty much think over here that uh, it's just going to show a light curve that, say, looks like that with time. Okay? So as the eclipse proceeds, you first, if this star is darker than this one, then you're going to see something that's just geometric. Okay, so far?
Yeah.
Now, um, okay, I don't know why I'm seeing people's names on the whiteboard, but anyway, there's something else that's going to happen though. So again, let me use this as the example. If you have a binary, then presumably the stars are rotating. Let's just say for the moment that the two stars are rotating. It doesn't matter whether it's synchronous or not. We'll get into that very briefly. But let's say that those are the rotation axes. Now, as the eclipse proceeds, you notice something is happening. That the left side here, in the way I drew it, is going to be blue shifted and the right side is going to be red shifted. So from the line profile, you would think that if you look just at the primary star, you should see a profile that looks like that, where this is the wavelength and this is the flux. Okay, got it so far?
Yeah.
Now, the faster the rotation, that is the shorter the period, the broader this is going to get. This is more or less what you're going to see if you look at a rapid rotator. Now, that's when the two stars are very widely separated. One of them may be showing up at a different velocity. It may have a different it will have a different rotation frequency and rotational velocity, but never mind. This star, we'll call it B, and this one A. B is blocking now the blue part of the line. So this part disappears. Then when it's in the middle of the profile disappears. It gets weaker. Then the line shifts when you're on the other side of the eclipse over here, because now you're blocking the red shifted side. Okay? So now you've got a velocity that's weighted to the red first and then to the blue on the other side of the eclipse. So if we measure the radial velocity from the line profile as a function of time, as the eclipse proceeds, namely that, the velocity, remember that the orbit is this, okay? That is, there's the line of centers. So at first, we have a radial velocity that has the star coming toward you, then the eclipse, and then going away. Okay?
Yes.
So we would think that the velocities would look like this. Blue shift to red shift. Eclipse is here. Except because of the geometric effect, we see that. First, it gets more red shifted, and then it gets more blue shifted. So What this implies is we can measure not just the rotational velocity of the star, but we can see whether it's rotating at the same frequency just from looking at the line profile, from looking at the way this shape changes. We can see whether the rotations are synchronized or not. That's damned important because if the two stars are sufficiently coupled that they have the same rotation frequency, then this also drives circulation in their interiors, especially if it's short period. Okay? We can determine that from simply looking at a spectrum as a function of time. It's called the Rossiter-McLaughlin effect. It's a very basic effect in binary stars, but you need a spectrum to do that. The resolution you need is going to depend on the period. If you're looking at a short period binary, of which there are lots, then you may be able to get away with a lower resolution. All you need to know is what the velocity amplitudes are. So if you want a resolution of 10 kilometers per second, you'll probably need at least a resolution of, 10 to 20,000. In other words, you need in a shell. But you might still be able to see the changes in the profile, even if you had something a factor of 10 lower. Depends then on your signal to noise. Okay?
Yeah.
All of that is accessible. Now, another example, again, using binaries. You'll have to forgive me. I'm just now, I'm just getting used to using this kind of whiteboard. So there's our star. Now, we'll imagine that this is a very extended atmosphere. And we have, so it's a giant, and we have this little dit of a B star next to it. So this is a B star, and this is, say, a red giant. Now, one thing we know about giants is they have really extended atmospheres. So if we have an eclipse, if the B star goes behind the red giant, instead of seeing the eclipse like that for the B star, it's going to do that. Okay? Just like a sunset. The lower atmosphere will eventually become opaque, but that may be a very small portion here. We could have a traverse like this, where it's almost total, but we don't actually hit the photosphere with the transit. Now, this kind of system is called, after its prototype, a Zeta Auriga system. Spectroscopically, the reason I want to mention this is that you now have something that's almost a pencil beam being seen through this atmosphere. The eclipses take a long time, as some of you know. Years, months. You got a lot of time. In the spectrum, the line of sight may pass through individual structures in the atmosphere. If you have, here comes another example, if the star were pulsating, then you might actually see the waves moving out in the atmosphere because you've got this light source that's allowing you to look through it. You know this from experience every day when you see clouds moving against the sun, or you watch a sunset. As the sun is setting, You see it through different layers of the atmosphere. So if you've got strong stratification, the color of the sun changes. Well, in this case, if you looked at the spectrum at, say, 7,000 angstroms, you could see the change in the water vapor because you'd see the absorption from different layers of the atmosphere as the sun passes across them. Here, in some of these systems, we can see individual convection structures within the atmosphere. We can see the origin of the broadening of the lines. It doesn't take very high resolution, and what you're seeing in those cases is basically the curve of growth. You use different lines along the same line of sight, and you can see whether, say, the magnesium 1 lines are varying the same way as the sodium 1 lines. You can do comparative structures knowing that the atmosphere is homogeneous chemically. You can use that to determine if you've got enough lines of enough states. You can use that to actually probe the structure of the atmosphere. Why you need that is because when we observe red giants in, say, globular clusters, and we want to understand their abundances, we don't have the advantage of being able to see their surfaces. We have to make guesses on what the turbulent broadening is. This actually measures it. No guesswork. You can use this for several different systems, and more importantly, if you have good doctors and you live a long life, you may get to see multiple eclipses of the same system. If not, you can always put that in your will as a requirement for your next generations, that they just watch the eclipses over time. There are lots of famous examples of these. Zeta Riga 31 and 32 Cygni, uh, probably the most infamous is Epsilon Auriga, which is a 27-year period, but some of them have periods as short as a few years and can repeat. Again, you can do this even at low resolution because it's exactly the same as watching the sunset, which, since I've been talking for an awfully long time, let me finish with an exercise that I think you might actually enjoy trying. Um, it's a very, um, let's see. Okay. It's a very nice little exercise that you can try with low resolution that will probably bring you fame and fortune among your friends because you'll be able to tell them that you've actually determined the structure of the Earth's atmosphere. So you can talk about climate change and all sorts of socially important things, which astronomers usually don't get to do. At this time of year, there are a couple, or actually this summer, there are going to be a couple of really bright, very simple stars like Vega that for most of you will go nearly overhead, plus or minus like 20 degrees, except for anyone who's in the southern hemisphere, and I don't think we have anybody on today. But if you take spectra of the same object at different times of the night and simply take the ratio of those spectra, you will map out the opacity of the Earth's atmosphere. We can do that now because of CCDs, because your data is digital, where just a few years ago it would have been difficult to say this. You don't need to flat the spectrum. You don't need to do anything other than take the ratio of one to another, because if you're taking the ratio, the sensitivity of the instrument hasn't changed. The only thing that's contributing is the effect of the Earth's atmosphere. So if you use a star, you can simulate the same thing with the Earth's atmosphere that you would do with the atmospheric eclipse of a Zeta Auriga star. I urge you to try this, because by looking at the different parts of the spectrum in the blue versus the red, you're measuring different levels of the atmosphere and different components. The blue is dominated by Rayleigh scattering. That's why the sky is blue, which is molecular nitrogen and featureless. It just happens to become progressively more effective as a scatterer the bluer you go. On the other hand, in the visible, in the middle part of the visible, you have the bands of oxygen around 6,300. And there are also ozone bands in the middle part of the spectrum. And then when you go to the far red, those ones that I said are the curtain in front of the star, those are water vapor. Okay, also oxygen, but water vapor. So by looking at the relative change in the different parts of the spectrum with altitude of the star above the horizon, you know you're sampling different levels of the atmosphere. And so you can see the way that the water changes relative to the nitrogen and relative to the oxygen. Once you've done that, you can apply the same reasoning to any atmospheric eclipse, which means you've also understood how you get the spectrum and understand the spectrum of an exoplanet. With one simple exercise, you can simulate everything that currently is in the headlines. Okay? You live on a terrestrial, oddly enough, you live on a terrestrial planet. You may not want to admit that, but it's a way of astonishing friends, of telling them that they have been living all their lives on a terrestrial planet. And as soon as you've said that, you may lose your friends, but it's worth it. Because if you're talking about the use of JWST in a transit spectrum to get the abundances and the structure of exoplanet atmospheres, you will have done it, except you're inside it. So that is, in a nutshell, going through the whole panoply of what happens when you have stable objects. So take what we were talking about last time in non-stationary, and then consider that when you have stationary objects, you can do the same thing with stars that you can do with, say, people. That the reason you can do normal anatomy and taxonomic classification or taxonomy with animals is because they're basically stationary objects, and there are certain basic laws of structure that govern them. And it's the same thing when we're talking about stars. So, um,
A
I
quick
hope,
question for you, if that's possible at this point.
well, in fact, I think this is a very good point, because I've been talking at you for an awfully long time, and you've been amazingly patient to hang in there. So please,
Is it possible to do this with a spectrometer that has a resolution of R2000 in the
abs
red?
absolutely. If it, let me put it differently. If it weren't, JWST would be a bust because that's about the resolution they're working at. Um, HST is a high resolution instrument. JWST is not. It wasn't designed for that. It was designed to go faint, but not high resolution. So 2000 is more than enough to see the effect on the bands. And in fact, the exercise that I mentioned of looking in the broad sense was done with an ALPI, so it was done with 1,000. And I actually gave that a couple of years ago as an exercise in lab, using only 2 spectra, because it was a short night. But the trick is to use as long as you can. And actually, it works better at low resolution than high, because if you go to a higher resolution, like in a shell, you have a problem with the overlap in the orders and that you're not getting enough of the spectrum in a single order. When you work at lower resolution with a grating to do this sort of thing, it's much, much more effective. So when JWST was building MIRSpec, the resolution is like 5,000. And that's more than enough to give you the band structure in the infrared. So yes, it's more than enough to give you the band structure in the visible.
Steve, a question.
Please.
When you were
Please.
talking about line broadening, you didn't mention rotational broadening. And I kind of had the sense that that was typically a bigger factor, obviously depending on rotation rate, than the pressure and turbulence
Um,
broadening.
well, not if you're hydrogen. Um, it depends on the opacity of the line and how deep you can see. And also on the rotational velocity. One of the things that unfortunately fortunately we still don't understand because it gives us some work to do, is that massive stars, and by massive I mean uh, say 4 or 5 solar masses and up, typically have rotation velocities of a couple of 100 km/s. That's the equivalent of saying they have rotation periods of a few days. The sun is a slow rotator. It didn't start out that way, but it is now. It's got a typical of the stars that we see that are evolved, that have stellar winds, coronae, and chromospheres. It's got a period of about 30 days, and that means a rotational velocity of no more than 10 km/s. On the other hand, when you look at the hydrogen lines and even the helium lines from the chromosphere, but when you look deep into the atmosphere, you can get to the point where the pressure broadening actually dominates. The wings of the hydrogen lines in stars like Vega have nothing at all to do with rotation. They're very, very much broader than that, and that's because of the atomic effect of having fluctuating electric fields in the vicinity of the emitting atoms and absorbing atoms. If the system is a close binary and the stars are tidally locked, then the rotation frequencies will be the same by definition. The larger star will have a different broadening than the smaller star, and that's something you can tell. Now, one other example. So to go to a new whiteboard, hoping that this will show up. Okay, so you see the whiteboard?
Yeah.
Okay. Take a contact binary. Being in Italy, I would call this a scamorza. And you clearly have stars with two different masses. I mean, this is a classic W Ursa Majoris star. Um, the center of mass is probably here in the way that I did this. So this star and this star, which sit inside a common envelope, have different rotation speeds. The lines that are coming from this surface are narrower than those coming from this surface. And the result is that the star has a profile in absorption that looks like that, where as the system orbits, they switch position. And you can actually get the radius ratio just by noting that the lines themselves have different broadening. It's the only system where you can do this uniquely. There's a lot of physics associated with that is connected with the surface actually being uniform temperature. Something, in fact, we don't understand well at all. But if you have, say, two stars in a detached system that happens to be synchronous, so they're close enough that they've synchronized, then again, you'll have different rotational broadening for one of the stars than the other. This one will be narrower lines than this one. Great example of such systems are those called ARAS Canis Venaticorum stars. So RS CVN, which happen also to have star spots on them. Okay? And so as the star rotates, the spot will produce a glitch on the profile, either in absorption or emission, depending on what you're looking at. And you can do the same thing with the W Ursa Majoris stars. You can map out the surface because they're rotating. Okay? Now that's in the case where the rotation is dominating the broadening, which for cool stars means periods of, say, 5 or 6 days, which means they're tidally synchronized. For slow rotators, for that is where the lines are narrow. Then, so like, what the best example I can think of is Vega. It's got an intrinsic rotation speed of hundreds of kilometers per second, but it's one of the narrowest line stars in the sky because we happen to be looking right down the pole. And in that case, we actually see the line dominated by the pressure broadening, not by the rotation. If we were at 90 degrees to it, we would see the line completely smeared out by the rotation.
Yeah.
Now, it gets worse, guys. If if an object rotates rapidly enough, then you know from taking water balloons and spinning them, which I hope you did in your degenerate youth, it distorts. And like a pizza, if you spin it in equilibrium, it expands and thins. So stars do the same thing because they're in pressure balance against their self-gravity. And a rapidly rotating star isn't spherical. So it doesn't have uniform gravity, and it doesn't have uniform temperature, and it doesn't have uniform pressure gradient, and so it doesn't have uniform ionization. So the way we understood finally, for example, that Vega is a rapid rotator viewed pole on, is that the lines that are formed in the equator have a different ionization than the ones that are formed at the pole. And they're in the same spectrum. That's why when we talk about stellar classification, it is very important to realize that it depends also on the prototype. Vega is the prototype A05 star. It's my last point. It is one of the weirdest stars in the sky, and if you looked at it at 90 degrees, it would not look like an A05 star. Okay? So the classification depends on the comparison with your sample. That is, it depends on the comparison with your standards. And as a final comment on this is why artificial intelligence applied to classification is exceedingly dangerous, because you're making the assumption that the training set is fiducial and complete. So it's exactly the same problem as doing spectral classification. One of the earliest examples, in fact, of AI applied to astronomy was in doing automatic classification. And it is a very, very limited and physically meaning from the astrophysical side, questionable. So I hope that helps with specifically with rotation.
Thank you, Steve. I think we can stop there. One more time, thank you very much.
Thank you all.
That is
And
so
Thank you, Steve.
appreciated.
have a very good weekend, and see you on the other side of the time change.
Okay,
Good
Thank
night.
you, Steve.
Thank you very much.
goodbye.
Bye.
Bye-bye.